In this section, we will talk about the MPLS Layer 3 VPN. MPLS Layer 3 VPN provides peer-to-peer connectivity between private customer sites across a shared network. On the screen, you can see a provider with an MPLS domain with customer A and customer B both using the same MPLS domain to connect their own private sites together. The MPLS domain is referred as the P network, and the customer sites are referred as the C network. Here we have the P network, which is the MPLS domain, and those are the C networks. And for example, for customer A, we have site 1 and site 2, and these sites are connected to each other by using the MPLS. So, in an MPLS Layer 3 VPN architecture, customer routers are known as the CE guys. That means the customer edge. And they do not run MPLS. In fact, they have no knowledge of MPLS, labels, or even VRF instances, which makes it easier for the customer to take the advantage of the benefits provided by a provider's MPLS domain. The customer edge routers connect to the PE, provider edge routers of the MPLS domain. So you can see in here is the customer edge, and here is the PE, provider edge router, and these are the P routers, and we will talk about this one also. Please notice that the PE routers such as PE-R1 and PE-R5 are the ingress and the egress LSRs for the MPLS domain. And the P router provider routers such as PR2, PR3, and the PR4 are the intermediate LSRs of the MPLS domain. The goal is to have a customer A site 1 and customer A site 2 exchange their local routing information over the MPLS domain and then forward traffic as needed from site 1 and site 2 over the MPLS domain. The same would be true for customer B site 1 and customer B site 2. Due to the nature of the MPLS Layer 3 VPN, overlapping addresses spaces between customers is of no concern. Therefore, customer A and customer B can be using same private IP address space. In order to support multiple customers, the PE routers need to use VRF instances to isolate customer information and traffic from other customers. A different VRF instance needs to be created for each customer, and the interface that connects to the customer's customer edge router needs to be associated with the VRF. The CE router and the PE router exchange IPv4 routes using a routing protocol such as RIP, EIGRP, OSPF, or BGP, and routes are placed in the customer-specific VRF table on the PE router. Therefore, from customer's perspective, the PE router is simply another router in the customer's network, but it is under the control of the provider. However, note that all P routers are hidden from the customer. Once the PE routers learn routes from the CE routers, the PE routers redistribute the routes into multi-protocol BGP, so they can be exchanged with other PE routers. When another PE router receives the routes, they are redistributed into an IGP and placed in the correct customer VRF instance so they can be exchanged with the CE router. An important point to consider is that the P routers are not participating in BGP. Only the PE routers are. They are forming an multi-protocol IBGP neighborship with each other and exchanging the routes using the underlying network that is built with an IGP. So the PE routers and the P routers are using a dynamic routing protocol to learn about all destinations in the P network, and only the PE routers are using multi-protocol IBGP on the top of that to exchange the customer routes. Now let's go back to overlapping IP address spaces. If all customer routes are being redistributed into multi-protocol BGP, how does the BGP handle identical network prefixes that belong to different customers? It uses a route distinguisher RD to expand the customer's IP prefix so that it includes a unique value that distinguishes it from the other identical prefixes. The RD is generated and used by the PE routers on a per customer VRF interface basis, and to keep things simple, the RD is used regardless of whether there are overlapping address spaces. So the route distinguisher is used all the time. The unique 64-bit RD is prepended to the 32-bit customer prefix to create a 96-bit unique prefix called VPN-v4 address. This VPN-v4 address is exchanged by the multi-protocol IBGP neighboring. So, check the example on the screen. The customer A VRF instance is using an RD of 1 column 100, right? And the customer B VRF instance is using an RD, and this is 1 column 110. When these route distinguishers are prepended to the IPv4 prefixes, the results are a VPN-v4 route of 1 column 100, this address, and 1 column 110 column this IP address. Now, let's say customer A also chooses to use 10.0.0/24 network and advertise it over to its other site. This is where the route distinguishers keep everything unique. Customer A would have a VPN-v4 route of 1 column 100 column 10.0.0/24, and customer B would have the route 1 column 110 column 10.0.0/24, and the following steps occur in this case. Step 1. The CE router and the PE router exchange routes using a dynamic routing protocol such as OSPF or EIGRP. In the second step, the PE router places the customer-specific routes in the customer-specific VRF table. On the step 3, the routes in the customer's VRF table are redistributed in the multi-protocol BGP as VPN-v4 routes. On step 4, the PE routers exchange VPN-v4 routes over their multi-protocol IBGP peering. On step 5, the PE router redistributes the VPN-v4 routes as OSPF, EIGRP, and so on routes into the customer-specific VRF table. And on step 6, the PE router and CE router exchange routes using a dynamic routing protocol such as OSPF or EIGRP. So let's go ahead with the MPLS Layer 3 VPN label stack. For the MPLS domain to forward traffic, a label stack is required. Specifically, 2 labels are required for traffic to be successfully forwarded through the MPLS domain. The first label that is attached to the packet is a VPN label, and the second label that is attached is the LDP label. When the IP packet arrives at the ingress PE router, the PE router attaches both labels. The egress router uses the VPN label to determine customer specifics about the packet and what should be done with it. The LDP label is used for label switching from PE to PE in the MPLS domain. VPN labels are learned from the PE routers over the multi-protocol IBGP peering, and the LDP labels are learned using the methods we explored in earlier sections. Let's say that when PER5, this guy, learns of 10.0.20/24 from CERB, it places it in the customer B VRF instance. It then redistributes it into multi-protocol BGP and thus creates a VPN v4 route of 1 column 110 and double column 10.0.20/24. This VPN v4 route needs a VPN label created for it so that the forwarding will be successful. In this case, PER5 assigns it the label 35, as you can see in here. This label is shared with PER1 over the MP IBGP peering they have. You can see in here it also has the 35 now. Now, anytime PER1 receives an IP packet that is destined for 10.0.20/24, it knows to attach the label 35 so the packet can be forwarded. However, this label is known only by the PE routers. Therefore, if PER1 forwards this VPN packet to PR2, it will be dropped, and as it has no idea what the VPN label 35 means. Therefore, the LDP label is needed to forward the packet from PER1 and PER5. So the figure on the screen shows how LDP is used to exchange labels that have been generated by the PE routers and the P routers. PER5 tells PR4 to pop the label, PR4 tells PR3 to use the label 52, and PR3 tells the PR2 to use the label 10, and PR2 tells to PR1 to use the label 99. Okay. So once the complete LSP is now ready to label the switch the VPN packet from PER1 to PER5. Now let's take a look to the figure on the screen. So now when an IP packet destined to 10.0.20/24 arrives at PER1 from CERA, PER1 determines that the packet needs a VPN label of 35, so PER5 will know what to do with the VPN packet, and an LDP label of 99 so that the VPN packet can be label switched through the MPLS domain. Once the label stack is complete, PER1 sends the label stacked packet to PR2, When PR2 receives it, it only examines the LDP label. Based on the LFIP, it states that the label 99 needs to be swapped to 10 and forwarded to PR3. So it does so. When PR3 receives it, it only examines the LDP label. Based on the LFIP, it states that the label 10 needs to be swapped to 52 and forwarded to PR4. So it does so. And when PR4 receives it, it only examines the LDP label, and based on LFIP, it states that the label 52 needs to be popped and forwarded to PR5. So it makes this happen. Now PR5 only needs to read the VPN label, which is 35, and based on the scenario, the label is removed and the VRF instance for customer B is used to forward IP packet to CERB router.